Hi, this is Kan-Lin speaking. I'm from National United University, Department of Energy Engineering. In the previous, we'll talk about the fuel test station, the function, and some kind of precaution of that. And this unit, we can talk about what each component of in a test station. Before this is a typical fuel cell test station in the university for the small watt. In the previous section, we talked about the hydrogenic, which is a very huge test station. This is typical. You can use for maybe 10 watts to anywhere to 100 watts. Those kind of test station. This will be sufficient. The test station had to at least had to satisfy those 5 functions. That means flow control, electronic load, temperature control, single cell, and the data acquisition. For the flow control, you can see on the test station the upmost those kind of the control box. They'll control different kind of flow, like hydrogen, air, and depends on if you tell it to pure hydrogen or even a nitrogen purge. Those kind of flow control will be controlled at this unit. And then second will be the electronic load. Electronic load actually control, you want to control had a constant output load or constant current, constant voltage. It's actually acting like a load to consume the output power generated from the fuel cell. And then the temperature control. The temperature control will be control the temperature at a different component, such as the inlet air, inlet hydrogen. And even you had a direct master fuel cell, you don't control the effluent and the flow of the methane or those kind of things will be in the temperature control different kind of component. And then the single cell. And the single cell is on the bottom. You can see the small single cell over there. You can even test a stack, smaller scale stack, maybe up to 100 watt. You can use that kind of test station. And then the computer will be used for the data acquisition or to control entire unit. This one can be, you can write a different program to control this unit. In our lab, we use LabVIEW. It's a vendor. He wrote this he used LabVIEW to write the control program to control this unit. And on the right-hand side over here is a hydrogen storage. It's a total enclosed. On the top, there's a pipe, so any leak of the hydrogen will be vented outside the building. But also had an alarm. If the concentration of hydrogen exceeds a certain level, it will raise the alarm. And then for this single cell, you can see the contact use the big brass over here to make the contact, because we try to reduce the contact resistance to minimum, and the cable use is much thicker. Even the output voltage only 0.5 to 0.7 volt. It's very low voltage. We still use a big cable and a contact, try to reduce any possible voltage loss. And then we not use the alligator clip, because alligator clip the easy rust, and then the contact area is much small, will generate a lot of contact resistance by alligator clip. And the fuel cell for a single cell, there's a heating pad will stick on the fuel cell to heat up to control the single cell temperature, because inside only one piece of electrode, the heat will be quickly dissipated by the graphite or the stainless steel case end plate. So we need additional heat to keep the electrode at the operational temperature. So, and also over here we had the thermometer to measure the cell temperature. But the cell temperature only we able to measure on the graphite or the end plate temperature. Inside the MEA, actually we cannot measure. There's no way we able to measure that. So we added the heating tube over here, not only the insulation, actually heating tube to heat up the inlet gas, because we find out that even we bubble through the water tank, the temperature can reach about 80 degrees, but goes through the pipe with the insulation. Actually, when it go into the fuel cell, the temperature may be dropped to 40 Celsius degree. So we need a heating tube to maintain the inlet gas temperature. And this one is a very big effect. Had to be very careful. Even don't think a small tube, the heat loss actually very huge. This is the electronic flow rate and the electronic load underneath that. And then this temperature control is able to control hydrogen, air, oxygen, cell temperature, hydrogen reheat. That's mean the heating tube where you just saw on the oxygen reheat, and even the direct mass fuel cell. And on the back or the bottom of the test station, there's a 2 tank. One tank for the cathode side gas. The other tank is for anode side gas. The dry and the cold gas was pumped through those water tank, and then the warm air will be coming out. And then this is a data acquisition system. You can control all kinds of temperature, flow rate, all this, and they also can monitor the cell current, voltage, those kind of things. Depends on how you write this program. It can be custom made. And important over here is you have to set up the stoichiometric ratio. That means the theoretical actual flow rate versus theoretical flow rate. Usually, this stoichiometric ratio is much higher, maybe greater than 1, because we need excessive air to go through the cathode side to make sure the cell performance, especially for the air, because if you make a aspect ratio, stoichiometric ratio is equal to 1, then you might end up with end of the cell, you might have a pure nitrogen. There's no oxygen at all. So the electron performance, the cell performance will be very low. Usually the stoichiometric ratio keep about 2 to 4, somewhere there. There's a different reactant supply mode on the hydrogen side. Also, this can be applicable to the cathode air side, but usually we talk about is on the hydrogen side, the fuel side, because fuel will cost money, and air, at least right now, is for free. The first will be the dead end mode, and then will be the flow through mode, and then recirculation mode. For the dead end mode, we'll talk about here. This is the dead end mode. On the left side is a single cell or cell stack. The red one is the electrode. The green part will be the membrane, and then the brown brown part is gasket for sealing, and then the gray portion is for the graphite plate. On the right hand side will be the hydrogen tank, and it goes to mass flow control. And then on the exhaust side, we had a pressure control, and then there's a control valve. Normally it's closed. Because this control valve is normally closed, so we call it a dead end mode. Let's see, for the gas, it will come in from the hydrogen tank, will be flow through the mass flow controller into the cell, and then in the cell is consumed. Is gradually hydrogen will be consumed, and then going to the valve will stop there. Inside the the cell, when the hydrogen consumed, the pressure will drop. So the hydrogen from the hydrogen tank will be released more hydrogen, or inside the cell theoretically will be filled with hydrogen at the controlled pressure P out. But in reality, because they maybe had water soak from the membrane to the anode, the channel may be blocked. So occasionally, probably need the air to blow through on the air side, try to clear out the channel, flow channel. So we may have a different type, we call it a flow-through mode. The flow-through mode, this part will be had a back pressure regulator. The hydrogen will be keep flow through the channel without any stop. So hydrogen will be keep go through the mass flow controller, flow through the channel, and then just exhaust. This type usually is for the smaller single cell test in a university academic or the research institute, smaller single cell, you might use that. For the stack, more than 100 watt or the kilowatt, usually will not do that because the flow through will be the first will waste a lot of hydrogen, and the second, the hydrogen exhaust you have to be treated properly, otherwise may cause some dangers. The third is a recirculation mode. This recirculation mode, unique about this is a test for the large fuel cell because it will not waste too much hydrogen, but with the proper recirculation, so the fuel cell performance will be much better than the dead end mode. The unique feature of the recirculation mode is that there's a pump or compressor connect to the fuel cell, so it will recirculate the hydrogen without exhaust. But this pump or compressor had to use explosion-proofed compressor pump. Cannot use a conventional pump or compressor because hydrogen you need to be airtight sealed. Make sure it's explosion-proof. With this kind of circulation, so the inside the electrode had a huge, good amount of air or the hydrogen flows through. Any water generated will be blow out the cell by the circulation pump. So the performance will be much better. But the pump or compressor also will be use some the electricity. So usually this kind of fuel cell is a configuration is used for the larger scale, maybe kilowatt fuel cell. They may equip with a pump or compressor for that purpose. So the hydrogen will be flow through the cell and then recirculate back.